Hi everyone, my name is Michelle Macauley, and I will be one of your instructors this quarter for breast ultrasound. Our class is pretty unique this quarter in that we're going to have both sonographers and mammographers in our class. So we're going to be learning a little bit about ultrasound basics, and we're also going to be learning a little bit about mammography basics. So I just asked patience on everyone's part. Some of this is going to be review for you guys, but review never hurts us. So most important part before we jump into breast ultrasound is making sure that we have the basics down. So this is lecture part B of ultrasound basics, and I apologize that the lecture is broken into different sections this quarter. I've added some new material this year to our PowerPoint from last year. So some of the lectures are from last year and some of the lectures are from this year, 2019. So we're going to be jumping around just a little bit, so bear with me here. So for this part of the lecture, we're going to talk about transducers. Transducers are the probe that we use to image the body. And what a transducer's job is to convert one form of energy to another. So a transducer has multiple little crystals in it, and the crystals are the ones that are responsible for converting the energy. So they convert electrical energy into a sound wave, and then a sound wave back into electrical energy. And this is how we get our ultrasound picture. There's many different transducers, as you guys can see from this image here. They come in all shapes and sizes, and we pick a transducer based on what part of the body we want to image. There's transducers that are for very superficial imaging in the body, and there's transducers that have greater penetration ability, so we use them for penetrating to deeper organs in the body. And then there's also intercavitary probes. So we have vaginal probes and rectal probes and also probes that we can use in the operating room so that we can get even closer to structures when we need to. Transducers are named for their shape. They're also named for their crystal arrangement, and then also the range of frequencies that they can transmit. So frequency is the number of sound wave cycles per second. All transducers transmit at different frequencies, and this determines how many cycles per second the sound waves are going into the body. And this also tells us how deeply this transducer is able to penetrate into the body. Today's transducers usually have a range of frequencies that they can penetrate into the body. So typically linear transducers transducers are higher frequency, and they typically can transmit anywhere from, say, about 7 megahertz, which would be 7 million cycles per second, all the way up to, there's even some nowadays that do 18 megahertz. And so these transducers, the higher the frequency, the less penetration that you have. And there's also transducers that have lower frequencies, which will give you better penetration. And lower frequency transducers are in the range of about 1 megahertz all the way up to, let's say, 5 or 6 megahertz. So for breast imaging, we use a high frequency transducer. Transducers don't need to penetrate as deeply into the body to get through all the breast tissue. And in the breast, we really need to pay attention to resolution. We care deeply about what the picture looks like and being able to distinguish small structures from each other and small differences in the breast tissue. So we care more about resolution than we do penetration in breast imaging. So we will always be using a high frequency transducer for breast imaging. So there's two basic groups of transducers. There's a mechanical transducer, and this is really more old school technology. And this is where you just have a single crystal, and the image is generated by a motor that moves the crystal. So nowadays we don't really see too many of those out there, but it is a type of transducer to be aware of. Most transducers today are what we call array transducers, and this means that they contain a series of crystals. They use various methods of focusing and steering, mostly electronic, to generate and create the image. And the crystals are laid out in very different patterns, all depending on type of transducer. The crystals are also fired in different sequences, and this also depends on transducer type. So next we're going to learn a little bit about transducer types. So first of all, this is a picture of our mechanical transducer, and this is where there's just one crystal. It's in a coin shape, and a motor rotates this crystal. And so it's a mechanical type of steering, meaning it's driven by a motor. You get a sector-shaped image from this. Sector-shaped image is an image shaped like this. So that would be our sector-shaped image. If there's any type of malfunction with a crystal with a mechanical transducer, the entire image is lost. So since there's only one crystal, there'll be a black image with no information. Next, onto our array transducer. So an array, this just means that there's a collection of crystals within a transducer, so more than one crystal. You can see here these blue circles here, these are our crystals. Transducers have many crystals in them, and arrays are defined by how the crystals fire, so what the firing pattern, and also how the crystals are arranged. And most transducers today are these array type transducers. So there's a couple of different ways that these can be categorized. First of all, by their horizontal crystal arrangement. So horizontal, think horizon, flat, side-to-side pattern. So crystals can be laid out in a horizontal pattern like this, sometimes just a single row of crystals. Crystals are also known as elements, so if you ever hear that word, that might also apply to a crystal. Crystals can also be what we call multidimensional, meaning that they have more than one row of crystals. So no longer is it just a horizontal transducer, but now you got to think in the vertical plane. And so these transducers have crystals in more than one horizontal row. And so multidimensional transducers are defined more by their vertical length. So how many crystals are arranged vertically and horizontally. And then we also talk about the crystal firing pattern. This is another way that we define transducers. So first, our horizontal crystal arrangement. This is where, again, we just have one row of crystals. They can be arranged in various shapes. And this determines what our field of view is. Our field of view is basically our ultrasound image shape. So there's many transducers in this category: linear arrays, convex arrays, sector arrays, annular arrays, vector arrays, and endocavitary arrays. So this is our bread and butter transducer, our linear array. This is what we use in breast imaging. And you can see here there's just a single horizontal row of crystals here, and they're arranged in a straight line. So every crystal sends out its own sound wave. So what happens is the ultrasound machine over here sends out an electrical charge, and the electrical charge hits the crystal, and the crystal changes shape, and it vibrates, and it emits a sound wave. And then that sound wave is going to go out into the body. It's going to hit a structure, and then it's going to return back to the transducer. And that returning signal we call an echo. And that's what ultrasound is based off of, all these echoes that return to the transducer. So when we have a linear array, these crystals are arranged in a straight horizontal line, and each crystal fires down the line. So when we're all done firing all the way down the line, we get a rectangular shaped image. So for a linear array, we have a rectangular field of view, or ultrasound image shape. Linear arrays are higher frequency transducers, anywhere from 7 to 18 megahertz, and they're used to image superficial structures in the body, so this is why we use it for breast imaging. The downside of a linear array is they are not able to penetrate deeply into the tissue due to the high resolution. And they also have a large footprint. So the footprint is the portion of the transducer that is touching the skin. So with a large footprint, it's tough to get to smaller areas of the body or to image just a small area, such as if you were going to image between someone's ribs. But with breast imaging, that bigger footprint actually gives us an advantage. It lets us cover more area on the ultrasound image at a time. Next is our curvilinear array. These are also called convex array. And with these, the crystals are arranged in an arc or a curve. So you have your crystals here. And as the crystals fire, they go out in kind of a fan shape. And this is what gives us our field of view, our sector field of view. So with a curvilinear picture here, we get a sector shaped field of view. So just like this. Curvilinear arrays are lower frequency transducers, anywhere generally from 1 megahertz to about 6 megahertz. They have a great ability to penetrate, so we use them in abdominal imaging and pelvic imaging and that type of stuff. The downside is they have a lower resolution than a linear array. Also, as these sound waves travel out, they wildly diverge. You can see the bottom of the image down there is much wider. Much wider than the top part of the image here. And that means that the deeper down that you go, you also have a decrease in resolution. So with increasing depth, there's less resolution. Where with a linear array, at all depths, you're going to have the same resolution because there's no divergence of that beam. Curvilinear transducers also have a large footprint, so a large portion of the transducer that touches the skin. Oops, wrong direction. Okay, so our next transducer is called a sector array. And a sector array has a little bit different crystal arrangement. So for a sector array, the crystals are all in one line, just like a linear array, but there's less crystals. So instead of having a long row of crystals, you just have a portion of crystals. And what these crystals are going to do is, instead of firing one at a time, like a linear array transducer would, they're going to fire in sequences. So they kind of fire in kind of groups. So for instance, this group will fire, and then this group will fire, and this is all in phases. So it lets it have just as many sound waves going out into the tissue. You get multiple scan lines or data from each crystal. And these pulses travel out in a fan shape, so they kind of create a triangular shaped image. So this would be our sector array. Just like a convex array, which is this one here, in the far field you get this divergence of the beams. So you do get a decreased resolution in the far field. Sector transducers are very low frequency transducers, so 1 megahertz to 5 megahertz. So you use these in places of the body that require a lot of penetration. And the advantage of them is, since they don't have such a long row of crystals, they have a smaller footprint, so a smaller area that touches the body. So they're really good for getting in between ribs and areas where you need a smaller transducer footprint. Annular array. So this is our next type of transducer. This is where crystals are cut into a ring shape, and each ring is a crystal. So each ring fires a pulse, and these are concentric rings, so they're smaller in the center and then get big as they go outward, so kind of like the rings of an onion. And this creates a sector-shaped image. And these pulses from each transducer ring, they're focused electronically, so you get high resolution at all depths, so you don't get that beam divergence artifact. The outer rings fire and they go deeper in the tissue, and so they get information from deep depths. The inner rings fire more shallowly and you get information from shallower depths. Now, if you get a broken crystal, you get a line of dropout. And this is something I forgot to talk about in the last slide. So with a transducer, here, you have your row of crystals. If a transducer crystal goes out or is broken, you don't get the pulse from or sound wave from that transducer. So on your image, you would have image all in this area, and then where there's no, when the transducer or crystal is broken here, this area of the image here, sorry, my thing zoomed out on me here. This area of the image right in here would have no information in it at all. So it'd be completely blank on the screen. So this area here would be completely black on the screen. And an area of blackness on an ultrasound image means that you've lost the image in that portion of the image. You also have vector arrays. So vector arrays combine the linear sequential technology. This is where crystals are arranged in a line, but they also combine the linear phasing technology, and this is the same phasing technology that a vector array transducer has, and this is where the crystals are fired in groups. So by combining both of those things, similar to a vector transducer, the same as a vector transducer, this is the transducer we were talking about just a minute ago, it produces a trapezoid image kind of shape, or triangular shape, some people call it. And this beam is steered electronically and focused electronically. So these are our basic 4 array transducers. So we have our linear transducer and our convex transducer here. We have our sector transducer. Here's our sector transducer. And then we have our vector transducer. Alright, so our next type of transducer is our endocavitary transducer, and we don't really have exposure to this in breast imaging, but just something to be aware of. This is a phased array transducer. So the crystals are fired in groups, but they're also arranged in a curve, so like a sector transducer. So those two technologies are combined. These are high-frequency transducers, 8 to 13 megahertz, and we use these in body cavitaries. So you can use them in the operating room, you can use them in the vagina, you can use them in the rectum. And this lets us get a close-up visualization of anatomy. Now, when a crystal goes out with these, not only do you get a line of dropout, but you're also going to get some erratic steering and focusing of the beam. So you'll notice right away if a crystal goes out. We also talk about the firing pattern of a transducer. This is another way that they're grouped or classified. So you can have sequential firing or phased firing, and this is the pattern in which the crystals fire. And this is all determined by time delays to the crystals. There's a thing in the ultrasound machine called the beamformer, and the beamformer portion of the machine implements all these little time delays. So for a sequential array, this is most of our linear arrays, the crystals are arranged side by side in a row, like this, and they can be in different shapes, like the curved shape, or they can just be in a line. Each crystal is going to create pulses that come out of this crystal, and all these pulses, as they come back to the transducer, are going to end up creating one scan line. These sequential arrays, the crystals fire one at a time. So down the row or curve or whatever pattern they're in. And you're going to have a large footprint with these since they're not firing in a phase, but they're firing single filely. And that's because each crystal is responsible for one scan line of the image. And these are going to provide either a linear or a sector field of view, just depending on how those crystals are arranged. And next you have our phased arrays. This is like our vector array. So this is where you have fewer crystals, so not as many in a row, and they're going to be fired in groups. So the crystals are arranged side by side, but you need less crystals. And so as they're fired in groups, this is called phases. Each crystal is going to create multiple scan lines. So you get to have a smaller footprint, the smaller portion that touches the skin, so you can get into smaller places like between ribs. All right, and then the crystals are going to fire at different angles. So you're going to end up with a sector field of view or a triangular field of view. All right, so we just have one more type of transducer to talk about here. And these are our multidimensional array transducers. And what that means is the crystals are not just arranged in a single line, but you now have a vertical distance of transducers, so of crystals. So you have crystals stacked vertically and crystals stacked horizontally. There's two basic types of transducers in this group. There's 1.5D transducers and there's 2D transducers. So for our 1.5D transducers, these contain 3 to 9 horizontal rows of crystals. So 3 to 9 rows. So you're still going to have a greater distance across horizontally than you will vertically of crystals. So there's still more a bigger horizontal row of crystals than vertically. And these are going to fire in phases. So the crystals are going to fire in groups. And what this does is the higher your row here of vertical crystals, the better elevational resolution that you're going to have. So this is the height of the ultrasound beam, the elevational portion of the ultrasound beam. Sound beams are not flat, they have height to them. And so this third dimension of the beam is our elevational plane. And so you'll have better elevational resolution the more vertical rows of crystals that you have. And then there's also a 2D transducer. So for this, you have the same number of crystals horizontally as you do vertically. So it's like a square. And what this allows us to do is it allows us to create a volume in imaging. And so we use these to do 3D and 4D type imaging. And there's going to be steering and focusing not only horizontally, but also vertically. So you're going to get increased lateral resolution and also increased elevational resolution. So there's a lot of advantages to these multi-dimensional array transducers.